welcome to lecture 11. So, we will talk about environments today after briefly recapitulating what we did in the last two lectures. So, in the last lecture we discussed the notion of bindings, and I said that in general we are talking about identifier value bindings in the case of constants, identifier location bindings in the case of variables, and in the case of updations, normally assignments, we are talking about location value bindings. So, I also said that you could pragmatically speaking, bindings are such that you could decide to stretch out a binding. For example, you could actually split up an identifier location binding into an identifier relative location binding and then a relative location to absolute location binding, and do it in a sort of temporally decentralized manner. And so, depending on the time at which you do various kinds of bindings, you might either have early bindings, late bindings, or somewhere in between. Now, bindings by themselves are a pragmatic matter in the sense that they really depend upon the implementation, but there is a certain core of bindings which is not pragmatic, which is a semantic matter, and that is just the fact that there is something known as a constant and that a constant declaration is somehow different from a variable declaration. That is a semantic matter. Okay. So, how you actually do the bindings is pragmatic. For example, if you take a language like Pascal and let us say type checking in Pascal, there is absolutely no guarantee. I mean, so that is also the typing of a variable or a typing of an identifier is also a binding. There is absolutely nothing in Pascal, in the definition of the Pascal language, which says that you should do your type checking only at compile time. In fact, there is nothing about the language which really specifies that you should actually only design a compiler. I mean, you might as well design an interpreter if it suits your convenience. However, the language has been designed in such a way as to make compile time checking sort of easy. For example, the name equivalence and so on, and the fact that you have to declare before use, they make compile time checking easy. So, normally, most Pascal compilers would try to do as much of the type checking at compile time, so that the overheads do not run into execution time. I mean, that's an execution. I mean, so it's a pragmatic issue in the sense that you want to make executions faster than they are, as fast as possible. Whereas it's not the case with languages like Snowball, Lisp, and so on and so forth, which want to produce an extreme of flexibility. So, they delay all bindings right up to the end, and they think of them, and it is all done dynamically, but it is still a pragmatic matter. There is absolutely no reason why you can't do some bindings earlier. Okay. So, what we will now like to look at is a semantic specification of certain kinds of bindings, especially the creation of environments, the processing of declarations, and how they affect the rest of the language. So, let us briefly go through the previous lecture. So, we had defined an expression language of this kind, in which I had explicitly forbidden identifiers. Okay. So, even the so it was a pure expression language consisting of just numbers, right. So, this production I was absent, and the reason is that an identifier has a meaning only if it has got some binding. So, what it means is that we can talk about the meaning of an expression containing identifiers only after we have obtained a meaning of the identifier in terms of some bindings. In this case, it is an identifier value binding that we are looking at. So, that the expression does not have a value, the meaning in our case mostly represents the ultimate value that an expression is going to have, and the expression does not have a value till the identifier has a value, right. So, we look at this, but we will look at it in a slightly more holistic fashion. So, let us also look at the language of expressions. So, the transition system. So, I assume that there is a set of expressions capital script E and a set of numerals script n, which is this. So, this script E is the set of all integer valued expressions E. I use small letters normally to denote that I am not dealing with the syntax of the language as considered by the non-terminals in the language. So, the capital letters here, the capital E's here denote non-terminal symbols of the grammar. The small e's here denote the syntax trees, that means there is some processing which has already occurred, okay, if you want to look at it pragmatically. So, I am really looking at syntax trees rather than the actual syntax of the expression. So, which means there is no ambiguity. So, I will try to maintain this distinction as far as possible, and similarly n is the set of all numerals in the underlying machine, and we defined a transition system with the set of all configurations being the set of all expressions, the terminal configurations being the set of numerals, which by the way are a subset of the set of expressions, yeah, and we defined the three rules which actually give us a left to right evaluation of expressions, right. So, now in an expression language which contains identifiers, we will take a simple language with declarations very similar to what is obtained in ML, okay. So, right here, so right now I am not too worried about types. So, I have simplified the syntax a bit. In actual ML, if this identifier is has got a value, then you would write let val I equals E in E end, okay. But since we are not dealing with anything else except values, I have removed the keyword val, okay. So, the language of expressions is just consists of this and an expression of this form, right, where of course there is a declaration hidden inside that expression, okay, and there is a declaration means that there is a binding occurrence of that identifier, and that declaration is itself expressed in terms of an expression E, and then if you have a binding occurrence, then you have a scope for that binding occurrence which is given by the complete expression, right. So, the identifier I might occur in the final expression E as an applied occurrence. So, informally what are we saying? If you look at this expression, what we are saying is that this expression is really our ultimate goal. The value of this expression is what we want, that is the meaning that we want. However, this expression is too complicated, for example, and so we have used an identifier inside that expression, and the meaning of that identifier is somehow syntactically represented by this declaration, right. So, the meaning of this entire expression is really the meaning of E, which contains which might contain possible occurrences of this identifier I that has been declared here. The identifier I of course has a value which is given by another expression, okay. So, you could simplify these things, but by for example replacing all occurrences of this identifier I by this expression E. and you would get a simple expression in the language. However, as you must have seen through some of our ML programs, it is always a good idea to allow for such declarations, such namings, because very often they have a meaning that is associated with a problem domain, and you would like to separate out those things. Instead of writing one long monolithic expression, you would like to split up the expression into various parts that are somehow logically connected with the solution of the problem. Okay. So, the identifiers here in ML could actually be variables and function names, but for the present we will just consider variables. And ML being a functional programming language, the notion of a variable is really that of an identifier value binding. And the reason I am not going directly into PL0 declarations is because the constant declarations in PL0 are very much like the variables in ML. Yeah. So, they both share the same kind of binding characteristic, the same semantic characteristic, that a variable in ML is just, in an ML program, is just a value, and so is a constant in a PL0 program or in a Pascal program. So, it is just a value. Okay. So, we look at this declaration, we look at the whole expression language. And what is an ML program? An ML program or an ML like program is really just one expression. So, if you look at the ML programs that we have looked at, that we have already seen, you can think of them as being, you have a collection of functions or values, declarations, and then you have a function, and that is what is compiled. Then you have an expression whose value is evaluated in that with those functions. So, you can think of any ML program as consisting of a let with a huge number of declarations, and finally an expression which has to be evaluated. What happens in the case of an ML session is that the outermost let, in and end are considered implicit, and it is hidden, and you do not have to explicitly write it. But you should think of any ML program or any functional language, the same holds in scheme too. In any functional language, you can think of the entire program as being enclosed in a huge let, in, end. And since it is an interactive program, what you do is, the outermost let, in and end are considered implicit, and you just, after having compiled all the declarations, you just give an expression to find a value. But each call to an expression there is really like having an entire program which is with all those declarations enclosed in a let, in, end. Yeah. So, so what we are doing right now is actually fairly general. So, let us look at the notion of identifiers, and so as in any area of mathematics or logic, we have to define when identifiers are free. Yeah. The notion of binding means that an identifier gets bound to something, okay, otherwise it is free. And what is the meaning of free? Given a certain expression or a sentence of a language, the free identifiers are those which do not have any declarations in that sentence. That sentence is supposed to be part of, let us say, a larger sentence in which those free identifiers will get a binding. Okay. So, a free identifier is one, given a sentence, a free identifier is one which has only applied occurrences and no binding occurrences, right. So, we can define the notion of freeness of identifiers by looking at the structure of the syntax tree, and we can define it by induction on the syntax tree. So, if you had, so let us look at our grammar for expressions, and we will follow the syntax of this grammar as closely as possible. So, you have this set of expressions, okay, and the notion of free identifiers is that given any numeral corresponding to this production, given any numeral, the set of free identifiers in it is empty. So, if the set of free identifiers is a set of names that occur in it without a declaration. So, this in any integer value, for example, the set of free identity, I am sorry, given any identifier which is also an expression, it is the singleton set of identifiers. Given any expression of this form, with this little o being the root operator of the syntax tree, the free identifiers in this expression is just the union of the free identifiers in the individual components. And if you have a let construct, then the actual expression value that you are interested in is E2, and the free identifiers of this entire expression, a let construct is a complete expression, the free identifiers of this are just the set of all free identifiers in E1, since you are using probably some identifiers in E1 to define this identifier I. So, it is a set of all free identifiers in E1, and this I will presumably be used in E2, which is the whole purpose of having a declaration of I. However, this any occurrence of I here is an applied occurrence which has a binding occurrence here, and so I is not in the free occurrences of, is not a free identifier of this entire expression. So, this is by the way set difference or set subtraction, if you like, yeah. So, the set of free identifiers in this entire expression is really the set of all free identifiers in E1, E2 excluding I, okay. Similarly, we could define the set of bound identifiers, and it follows a similar pattern. The set of bound identifiers is also defined by induction on the structure of the syntax tree. So, numerals and simple identifiers, a simple identifier is by the way free, yeah. So, the numerals and simple identifiers do not have any bound identifiers in them, and the set of bound identifiers in an expression of this form is just the union of the set of bound identifiers in the individual components. Note, however, that these two expressions could have the same identifier bound in different ways. I mean, you could have an x inside E1 with a declaration for x, you could have an x inside E2 with a declaration for x, and the two x's need not be the same, yeah. However, let us look at that later. So, and in this case the set of bound identifiers is just the set of all bound identifiers in E2 union the set of all bound identifiers in E1, and of course in E2 any occurrence of I would not be considered bound, and so that has to be bound separately, right. And the set of all identifiers of an expression is just the set of all free and the set of all bound identifiers in it, yeah. So, the notion of bound identifiers has to do with already possessing a meaning which means that the expression can be readily evaluated. Yeah. So, the notion of so it is important to keep this for example, if you were to the notion of freeness and bound identifiers exists in all programming languages, okay, either through implicit bindings or explicit declarations. So, if you look at a completely closed program, if you look at a complete Pascal program, there are no free identifiers except those which come from the global environment of the Pascal runtime system. Okay. So, what are the identifiers that come from the global environment of a Pascal runtime system? All those library routines which are readily available. So, if you look at just a complete Pascal program, supposing you do not use any of the libraries, library routines, then the complete Pascal program has absolutely no free identifiers. The program heading has a name, and that is itself a defining or a binding occurrence of that name, of that identifier. Otherwise, every other identifier, if you are not using any of the library routines, every identifier is declared before use. So, if you look at the entire Pascal program, there are absolutely no free identifiers, all identifiers are bound. So, that means every identifier in that Pascal program has a binding occurrence which defines it completely, right. So, a complete program of this kind which has absolutely no free identifiers is called closed. Yeah. So, for any in any language which has identifiers, which allows identifiers, you can talk of a closed sentence of the language as one which has absolutely no free identifiers, and a ground sentence is one which has absolutely no identifiers at all. So, in fact, the transition system we considered for the expression language without any identifiers consists of only ground expressions, right. So, closed and ground, these are two important terms which occur in any formal language, whatever may be the formal language. Yeah. So, so the important thing is that a closed sentence. So, if you look at a complete Pascal program, since there are no free identifiers, the program itself can be executed in an empty environment, because there are no identifiers which require to be given a meaning from outside. A free identifier is one which gets its meaning from outside the sentence that you are currently looking at. So, in a complete program, since all identifiers are bound, they get their meaning from within that sentence, and therefore, a complete program executes in an empty environment, right. A ground sentence does not require an environment at all, since there are no identifiers which require bindings. Yeah. So, what we have, so our expression, our transition system for expressions actually gives us a transition system in an empty environment. So, I have not actually mentioned that. So, since we considered only ground expressions without any identifiers, they obtain their meaning in an empty environment. Okay. So, these things are these things are actually quite simple. I mean, after all, if you ask me, what is the value of ax square plus bx plus c. Well, clearly I cannot give you that value unless you can give me a meaning, you can give me a binding for a, b, c and x. Okay. So, under the assumption, so given that a has a value something, b has a value something else, c has a value something else and x has a value something else, then this expression has a meaning in that environment. So, that environment is just the name value bindings for a, b, c and x, right. So, it is just a set of such equalities, name to value equalities. Yeah. So, we will define the notion of an environment for this simple ML like expression language. Given a set V of identifiers, at this moment the only kinds of identifiers we are interested in are identifiers which take integer values. Yeah. So, they are like the variables in ML. An environment rho over the set V is just a mapping from capital V to the set of numerals, right. So, you can think of an environment as actually a list or more accurately a set of values. This should be a set of variable value bindings, and we can look upon for any given collection of variables V, we can look at all the environments that are possible. So, I will use ENVV to denote the set of all environments over capital V. Very often this subscript V, the subscript V will be omitted when it is either understood or it is not important and so on and so forth. Yeah. Otherwise, we are always considering an environment with a given set of identifiers. Of course, that set of identifiers could be extendable, right. So, let us look at the declaration language. We could actually extend its language further. So, since declarations have a semantic meaning completely different, they are logically a different entity from expressions, it is a good idea to abstract that out as a separate non-terminal, which is something we have already done. And in fact, by abstracting it out as a separate non-terminal, we have also, I mean the language of, for example, PL0 also gives them a separate syntax and separate reserved words to make it clear that it is semantically a different logical entity from that of expressions or commands. So, once you have this, there is absolutely no reason why you should have only one identifier declared there. You could, for example, have several identifiers declared. So you have a separate declaration language whose basis is a single declaration and you can recur on that basis and give sequences of declarations, which is what happens in most programming languages, right. So, now what we have is that we have a programming language, a functional programming language whose main non-terminal is the language of expressions, and there is an auxiliary language within it which is the language of declarations. And if you look at the dependencies, so for example, the expression language allows for declarations inside expressions, and declarations in turn allow for expressions inside declarations, and they both allow for identifiers, right. So there is, as you can see, there is a certain circularity in the entire definition, which is what happens when you apply these things inductively or recursively. Yeah. So, for the moment we will not talk about this, but it has some meaning that I will explain later. So, our language, whatever we write in green is really our language, right. So, let us look at some quick examples. For example, so a typical sequential binding could be of this form: let pi equals 3.141 semicolon 2 pi equals 2.0 star pi. The semicolon is very important in the sense that you are in a sequential declaration, what you are, the sequencing might be important. What you are explicitly saying is that the second declaration might actually depend on definitions given by the first declaration, as in this case. Very often, of course, this dependence is not there, in which case they could actually be written in either order. This is also typical in Pascal. For example, you could have a constant declaration of pi semicolon something, another constant which uses the previous declaration of pi in the evaluation of its value. So, you could have a complete expression in a constant declaration, provided all the identifiers in that expression already have been declared before, right. Okay. In the case of Pascal, of course, they should all be constants too, they can't be variables, but for the moment let us not worry about that. And the actual expression whose value you are interested in is this, where of course this identifier radius is free in the entire expression, and presumably this expression has been pulled out of some context in which maybe radius has a binding, but this is an expression in itself and we are not too interested in context sensitive syntax. So, what we will assume semantically is that this radius, in order for this expression to have a value, which is what we mean by the meaning of an expression, it is necessary that there be an environment in which radius has a value, and once that is done, I can evaluate this expression, right. So, you can have sequential bindings like this, you could also have nested bindings like this. So, the actual expression you are interested in is, let us say, A star h, where h is free. So, the value of this A star h is what you are interested in, and however you required, since the expression, well, presumably was getting too complicated, you had to define this A, and in order to define this A, I had to define this pi. Okay. Again here there are these two identifiers, there are two occurrences of the identifier R, which presumably was which are free, and so they must, so it is not possible to evaluate this entire expression unless R and H are given some value from some external environment, unless they have been declared somewhere in the context. Yeah. So, you could have nested bindings too, okay, and this is in fact allowed in ML. By nested bindings, what you are doing is you are really localizing this identifier A. It is local only to this scope between this let in and end. The identifier pi is local to entirely this scope. Yeah, right. So, since such a construction is possible because of the fact that an expression can have a declaration in it, a declaration can have an expression in it, but if this expression, if this is a full fledged expression, there is absolutely no reason why it cannot have a declaration inside it, right. So, we have to keep in mind the fact that such things are possible, when we evaluate, when we define the semantics of this language. Yeah, right. So, the localization of new environments is something that we will define here. So, let us define an operation on environments. So, assume you got some variable sets V1 and V2 whose union is V. Note that I am not assuming that V1 and V2 are necessarily disjoint. Okay. V1 and V2 could have some common identifiers in them. After all, as we saw in bound expressions, there was absolutely no reason why the same identifier could not have been bound in different bound differently in different localities, in different sub expressions. Yeah. So, let us assume that rho 1 is an environment over V1. This is a short form notation to indicate that rho 1 is an environment over V1, rho 2 is an environment over V2. Then we will define this operation called rho 1 with rho 2 within brackets. Yeah. We will define this as an operation. I am using light blue always for rows because for environments, because I have so far not actually defined what an environment means in concrete terms. I have taken out the minimum information that I require. So, as far as I am concerned, an environment is not a data structure, it is an abstract entity which later, after you have semantically specified all that you require of an environment, you can come out with a suitable data structure to represent environments. Okay. So, the normal coding conventions I will follow throughout are that anything that is blue is likely to be somewhat abstract, up in the sky somewhere. Anything green is very programming language oriented, brown is something that is quite down to earth, maybe related to the underlying virtual machine. Black, actually I have black is something that I often use for explaining things, which is actually goes beyond the sky into outer space, which is very dark, but it could also be something very deep down inside the earth, you know. So, some things could be as black as coal. So, I have a sort of a schizophrenic view towards black, but otherwise I will use this sort of color coding throughout. Yeah. So, I will define rho 1 rho 2. So, that is a new environment. So, this is an operation on environments which creates a new environment for each identifier I. If I is in V2, then the binding given by rho is the same as the binding given by rho 2. Okay. For all identifiers that occur only in V1 and not in V2, the binding given by rho is the same as the binding given by rho 1. Yes, and we are only considering the set of identifiers in V1 union V2. So, there is no other possibility, right. So, note that this is an asymmetric operation and that rho, so we can call it as rho 1 updated rho 2 is not the same as rho 2 updated rho 1. Yeah. So, we will be requiring this operation, as you will see, right. So, we will define the operational semantics of this. Since as I said, if you look at our grammar, expressions require declarations, declarations also require expressions. So, we cannot isolate the two completely. So, any semantics of the expression language will depend upon a semantics of the declaration language, and a declaration and any semantics of the declaration language will depend upon the semantics of the expression language. So if we have to give a semantics now, we have to give a holistic semantics including both expressions and declarations, and we have to make it complete, right. So let me quickly go through this and I will explain the finer points next time. Yeah. So I will start with, in exactly the form we have our grammar, the main language is the language of expressions. So I will start with the transition system for expressions. Now I have a difference, I have to consider only all those expressions in the language over some set of variables v. Of course very often I will just get rid of this v. So the set of all configurations of expressions is just the set of all expressions over v, and the set of all terminal configurations is still the set of values, because the meaning of an expression ultimately is just a value, right. Okay. And we will define this transition relation under the assumption of an environment. An expression which contains identifiers does not have a meaning unless each of those identifiers has a meaning. In other words, the expression does not have a value unless each of the identifiers has been given a value. So that value assignment to the identifiers is going to be in this environment row. Yeah, right. So I will just quickly go through the modified forms of these, of the transition system. So the first thing of course is that we have to introduce an axiom which says that in any environment row, given, that means an environment is just a value binding to each of the identifiers, right, it is just a set of value bindings. An expression which is just an identifier which is allowed by our grammar has a value just given by the binding, right. So given any identifier, and note I said once before that our transition systems are syntactic or symbol manipulations, and this symbol manipulation is that you, whenever you encounter the identifier I, this transition indicates that that is really being replaced, if you like, by the value given by the environment. It is still symbol manipulation, but symbol manipulation in the abstract, right. So the other three rules are exactly as we had before, except that now we have to bring in the environment, because we really cannot the rule E1 does not really require an environment. However, the E1, an application of E1 would often in the general case would never be complete without an environment, because E1 would be applied only after you have successively applied E3 and E2 several times. Just go back to our basic example of our transition system. So what would happen is we are specifying a left to right method of evaluation. So you would be applying, so given an expression of the form E1, some binary operation E2, you would keep applying E3 till the left hand operand became a constant, became a numeral. Then you would start evaluating the right hand operand till that became a constant, and then you would just evaluate this constant, right. So there would be several applications of E3 till the left hand operation became operand became a constant, then several applications of E2 till the right hand operand also became a constant, and then an application of E1, right. So if you look at the syntactic application of these rules in a typical large expression, that is what would happen. So what in the case of this, and in the case of the introduction of identifiers, what would happen is before applying before an expression like E1 became a constant, there would have to be an application of a call to an environment somewhere. to replace the identifiers in it by appropriate constants or literals, if you like, right. So, there would be interspersed in this process of execution would be applications of E naught where identifiers are replaced by constants, okay, and those and all of them require this environment row, right. So, however, so this is only for the basic language of expressions which does not contain any declarations. So, we have to still give a meaning for the let construct, and the let construct is something like this. So, let's look at this. So, the meaning of a let construct of this form is really the value of E. However, the value of E depends upon this declaration D inside the let construct, and so there is no way I can evaluate this expression E till I have evaluated this declaration D, and evaluating the declaration D means creating fresh bindings. So, which means that this expression can make some progress only if the processing of this declaration can make some progress. So, if this declaration moves from from D to some D prime, I have not yet specified what it means for a declaration to move from D to D prime. That is something, since we are looking at things in a top down fashion, it will come later, yeah. And supposing, so several applications of E4 will finally reduce this declaration to some environment rho prime, okay, and now I am in a position to evaluate this E, and I can evaluate this E, and this E can move to some E prime. And how do I evaluate this E? I evaluate it really in the environment rho updated with rho prime. However, this entire expression, the let construct, really is executed in the original environment rho with which it came, which in the case of a completely closed program, this rho would be the empty set. But in the case of a program which is not completely closed, an expression need not be completely closed, it would execute in some environment rho. So, once the declaration has been completely evaluated to produce an environment rho prime, this expression can be evaluated, and the evaluation of this expression proceeds in this modified environment, in this updated environment rho prime, okay. And now in this modified environment, essentially what would happen is, if there are no let constructs within E, if there are no nested bindings, then you would be applying rules E naught, E1, E2 and E3 to finally evaluate this expression by several applications. And having done that, what will happen is that you will be left with a constant finally, and the result of this expression is just this constant, right. But note that the entire let construct, really its environment is only rho, and the updation rho prime is really a temporary change in the environment, and in that sense it is reversible, right. So, there is a reversible process. So, this temporary change in the environment is necessary in order to evaluate this expression E, but really the environment in which the entire let construct is being executed is in the original environment that it started out with, yeah. So, the environments, the updations of environments is a typical case of a reversible change, in the sense that if you apply these rules systematically, there is absolutely no reason why you should be left with a strange updated environment which is different from what you started off originally with. You always end with the original environment you started out with. In a completely closed Pascal program, you start with an empty environment, and after you have executed, you still have nothing more than the empty environment. The completely closed Pascal program executes in that in the original global environment, and as declarations come, new updations which are temporary are created, and as those scopes are exited, those updations go away automatically, right. Okay, I will stop here. I will continue again on the declaration transition system next time, and we will look at some examples.